Hello, we are group number one, confirmed by Daniel Morantes, David Ramos, and me, Sara Aguilar. Today we'll present a report regarding the fourth laboratory practice from the theory of composite materials. Here we have the table of contents about what will be discussed in this video. Before talking about the experimental practice and its results, it is necessary to know some concepts. What is a composite material? Composite materials are those formed by the combination of two materials in order to stabilize or enhance different properties that allow these characteristics to be improved when they're being used. Well, an example of a composite material is the matrix made by PLA and fibers. But what is PLA? Well, lactic acid or PLA is a thermoplastic polymer obtained mostly from corn or sugarcane, which makes it biodegradable. In addition to the latter, its most notable characteristics are its possibility of being recycled, its high mechanical resistance, its good wear properties, its easy processing, and low toxicity. However, it has some disadvantages of its use, such as very low thermal stability and low impact resistance. Uh, for this reason, it is common to use different mixtures with PLA in order to improve the characteristics that are not convenient for its use. In the case of this practice, graphite and rice husks were utilized. In addition, a mixture of polypropylene with cocoa was also used.
Well, now for the methodology, we'll first of all show you the research method we found in a paper. The objective of this paper was to estimate the conductivity of different materials. The first step was it was to obtain plates of the samples of interest with a specific area and thickness. It's important to mention that in contrast with the methodology we do in the laboratory, in this case, our samples was like complete plates of the material that we want to estimate the conductivity. And in the method that we use in the laboratory, it was just like filaments of the material. This is because the methodology that we do in the laboratory is a little bit easier than this one because it is easier to obtain just a filament and not a complete plate of a specific area and thickness. The second step is to assemble the measurement system that consists of an Arduino with a DHT22 sensor, a thermal imaging camera, and a wooden camera. The wooden camera refers to the external part of the system, and this wooden camera acts as a thermal insulator. This is just for like to block the other energy sources that could affect the system. The third step is to adjust the material plate through the measuring system. In this part, it is important that the dimension of the plate must be the same as the dimension of the Gurun camera, because if they are not the same, the material isn't going to adjust to the system. The fourth step is to turn on the heat source to start the test. In the paper, they use a light bulb, a conventional light bulb with a power between 60 and 75 watts. So in the paper, that was their heat source. The fifth step is to wait for the system to reach the thermal equilibrium to begin taking the data. Well, this part is another like factor that makes this methodology like more difficult than the one that we do in the laboratory because in this part, the thermal equilibrium it is quite important uh, to start taking the data, and we have to like wait like between 30 and 50 minutes to start taking the data. This means that this methodology is quite longer than the one that we do in the laboratory. And finally, the temperature is taken in the light bulb and on the outside of the plate with this kind of thermometers. It can't be used the other one, the conventional one that we use in the other lab, in the other methodology. Sorry. Now going through the methodology that we use in the laboratory, our samples in this case was four different filaments Well, like experimental materials developed in also in a laboratory. The first sample was made by rice husk and PLA, the second one by cocoa and propane, the third one by graphite and PLA, also PLA, and the last one was just a filament of copper, a normal copper. Well, now for the methodology that we carry out on the laboratory, the first step was to cut the filaments to a length of 9 centimeters. Well, it's important to mention here that we cannot obtain the exact 9 centimeters for all the filaments, because, for example, for the rice husk, we have a length of 8.7 centimeters. For the graphite and PLA, we have an 8.9 length. But for the calculation, we just rounded these values to 9 centimeters. The second step is to do the preheating of the heating plate to 120 centimeters. Well, also here is important to mention that although we preheat the heating plate to 120 degrees, we have to use a lot more, because to the filament, to the initial part, the part that was like pasted to the tape, it wasn't in the well in the desired temperature. It was like a little bit less, so we have to increase the temperature of the heating plate. The third step was to paste the filaments with the tape on the heating plate. As it is shown in the picture, the a corner of the filament was pasted to the heating plate, which is just normal tape. The fourth step is to define how often the temperature data will be taken. In our case, we decide to do in 30 seconds after the filament was pasted, 60 seconds, and 90 seconds. We decide those three times. The fifth step is to take the temperature of the filament at the defined time at each established point. What it means in the established point, it means to take the temperature in the different points of the filament, because here is the like the most important part, because in each different point of the filament, the temperature is going to be different, well, due to the fact the conductivity is not the same in all the filament. Well, we decide to do like every 3 centimeters, so we have like 4 points. The first one was the one that have the direct contact with the heating plate, and then 3 centimeters, then other 3 centimeters, and the last one was around 9 centimeters. It was the point that was like the farthest to the heating plate. And the sixth and last step was to perform the conductivity calculation with the data obtained. And to do those calculations, we have to we use this formula, and we have to estimate the conductivity height, taking into account the density, the the CP, and the first derivative of the temperature and the time, and the second derivative of the temperature. Well, also with the distance of the filament. Well, now for the results, we can see first the temperature of the filament versus the distance. These curves can show us the second derivative of the different data. This data is quite important when doing the estimate of the conductivity. And it is important here also the fact that the red line that is in both graph is the smoothed curve, and the blue points that are also in both graphs are the real points of the graphs. But when doing the smoothing of the curves by using curve feature and toolbox of MATLAB, the the estimate curve that MATLAB give us to a second degree polynomial is this curve, is this smoothed curve. The secondary rate also show us the inflex point of the data. We can see also the secondary rate. There is the the number there, the label there is below the both graphs. Here in this part is the temperature of rice husk and the temperature of propane and cocoa. In this second graph is the same of the as the previous one, but in this part we have the temperature of PL8 and graphite and the temperature of copper. We can see here also the second derivative below the graph and also the smoothed curve, and the blue points show us also the real points, and with no doing the you well with no using the curve feeder on MATLAB. Well, in this graph, it is shown the trend of the temperature throughout the pass of the time. We can see that the filament that had the highest temperature at that time zero was the graphite and PLA, and the one with the lowest temperature was the copper. We can also see that this graph has sense in terms of that when the time increase, when time pass, the temperature must decrease. This is due to the fact that the temperature of the heating plate and the temperature in the filament decrease throughout the pass of the time. And also it's important to mention here that this graph is based on the first derivative of all the filaments that I'm going to mention in the next part. And also in this graph, the filaments, the temperature of the filaments, in the temperature of the filaments are included all the 12 temperatures that we obtain in the methodology in the experimental part. And because this vector of temperature is it has a length of 12, including all the temperatures in all the times and in all the distance of the filament. Well, now you can see the first derivatives that I was mentioned before. What we have fourth derivative for each filament. Well, this is because we are trying to prove that the filaments that we are using are anisotropic, and well, we have these four derivatives because in each part of the filament that we take the temperature, we want to estimate the conductivity in each part of the filament with the by using the conductivity formula, we are going to prove that the filaments are anisotropic by using these four derivatives. These derivatives were obtained also by using curve feature in MATLAB, and having the slope of the curve and also the smoothed curve of the data that we have of each temperature and each distance. And that's all for the results.
The conductivity was measured in four parts of the filament. In the initial point, 3 centimeters later, other 3 centimeters later, and in the final point. The conductivity of these different parts of the filament is shown on these tables. In the rice husk and PLA filament, in the first part was minus 338.707 watts over cubic centimeter Celsius grade. In the part 2, 3, and 4 was 38.707 watts over centimeter cubic Celsius degree. In the propene and the cocoa filament, in the first part was the 461.6331 watt over cubic centimeter Celsius degree. Excuse me for the cat sounding. In the part 2 were 172.691 watt cubic Celsius centimeter degree. And in the part 3, this is an anomaly that is 1639 to times 10 elevated to minus 30 watt over cubic centimeter Celsius degree, and in the fourth, in the final spot, was over 12.945 watt over cubic centimeter Celsius degree. In the case of the graphite, in the first spot was minus 99.820 watt cubic centimeter Celsius degree. In the second spot was minus 64.801 watt over centimeter cubic Celsius degree. And in the third spot was minus 72.283 watt over centimeter cubic Celsius degree, and in the last spot was minus 84.854 watt over cubic centimeter Celsius degree. In the copper filament, the conductivities were 0.079 watt over cubic centimeter Celsius degree, 0.022 in the second spot, O minus 0.20 watt over cubic centimeter Celsius degree, and in the last spot was 0.012 watt over cubic centimeter Celsius degrees. Now we are going to talk about the differences between the methodologies, the proposed and the final methodology. The proposed methodology is easier to perform but needs plates of the material. In the case of the filaments of these structures, it's difficult to change the geometry of those materials. Also, the proposed methodology can measure the conductivity over just one point and in one direction only, downwards. The great virtue of the proposed methodology is that it was based on the American Society for Testing and Materials method. The ACTM is the organization of international standards that develops and publishes different techniques to measure the properties of different materials, in this case, conductivity. The final methodology was most effective for cylindric geometries due to the hex conduction over the z or the height dimension, because the height was put on the lowest point of the filament and we measured the temperature on different points of the z direction of the filament. Both methodologies, proposed and final, have great change of error because of the melting factor and the anisotropic factor, because we are assuming that the filament is isotropic. This means that all the properties are the same in every point of the material and in every direction, which is not true. And the filament, and we are assuming that the filament are not going to melt at certain temperature, which is again not true. We're going to review these factors more in detail later. Also, Guo finds a range of the thermal conductivity between 0.18 and 0.28 water metal Kelvin on the PLA with graphite, and the data characterize different types of copper filaments, finding a thermal conductivity of 2.94 watts meter Kelvin in a normal molded copper filament. There are significant differences between the literature and the results of the experiment. In our experiment, the calculated thermal conductivity was about the 0.289 water meter Kelvin, but in the literature there was a conductivity of 2.94 watts meter Kelvin. This is an error approximately of 69.94% of error. This is an enormous error for this property. This high error value is due to some factors that were uncontrollable in the experiment. The most important factor was the breaking of the filament, or the melting. The melting changed the direction of the heat flux. The filament, after its melt, was not touching itself at some point. This difficult the heat flux through the filament, and also the geometry was distortionated, changing the calculus of the Fourier law of heat flux. About the molecular explanation of this phenomena, the temperature, molecularly speaking, is movement. The conductivity is the capacity of a material to allow the movement transfer between molecules, as it's easier to the molecules to pushing between them, forcing and generating movement. The conductivity takes higher values. There are some components on the composites that can help the movement transfer, coupling inside the space between the molecules that the molecules left, easing this domino molecular effect. In the composites, other components can open more space between the molecules and even making an interface on the element A and the element V, and this interface generates a discontinuity in the temperature. This step is because the interfaces are in a certain distance, and this makes that the movement dissipates in this interface.
As it can be seen in the table of results of the conductivities obtained in each material, with the exception of copper, a great variation is seen in the conductivity values depending on the point at which the data used to calculate them were taken. This variation can be explained by knowing what anisotropy is, which is the variation of thermal conductivity with direction within a material. This may be attributed to differences in their structure or link direction. Likewise, this property is in itself a possible source of error in the calculation of conductivity, since the temperature taken at each point was the one found around the filament and not in the center of it. To sum up, we can conclude that the objective of the practice was reached, and it was observed that the methodology used for the experimental practice was better in terms of the easiness of getting the materials. However, while carrying it out, there were different error sources at the moment of collecting data. On the other hand, the one proposed by our group was easier to carry out, but it was more difficult to get the equipment necessary for doing it. However, the data collected would have possibly been better in terms of precision. In addition, it was found that there were other resources in the development of the practice coming from the deformation of the filament. It was also observed that the differences between the conductivity for the same material is due to the organization of its molecules, where an interface that generates a discontinuity in the temperature may be made. Furthermore, the anisotropic characteristics of the materials was important to determine why the conductivity behaved like that. It is also necessary for future experimental practices to propose another method to measure the conductivity of composite materials in a way that avoids the melting factor and allows a faster and more precise measurement of the temperature at each point. Thank you.